Hello friends, today we are going to see how to find out the sum of diagonals in a binary tree. So let's see the example. This is the binary tree and we want to find out the diagonal sum in this binary tree. So for finding out the diagonal sum, we have to traverse the diagonals in this binary tree at first. So for traversing the diagonals, we have a notation that is D, which denotes to the diagonal distance of each node in this binary tree. And we have to assign that distance, that is the diagonal distance, to each node in this tree. Let's see how to assign it. These are the three rules for assigning the diagonal distance. For root, diagonal distance is equal to 0. That is, D is equal to 0 for root. The second rule is for left child, D is equal to D of parent plus 1. So the left child of 1 is 2. So the D, that is diagonal distance for 2, will be 0 plus 1. So that will be 1. Diagonal distance of parent plus 1. So for 2 the parent is 1, so the distance is 0, plus 1 it will be 1. Now for right child, the third rule is for right child the diagonal distance is equal to diagonal distance of parent, means the diagonal distance remains same as that of parent. So for every right child the diagonal distance remains same as of parent. So the diagonal distance will be 0. It is same as parent. Let's go ahead and assign the distances to each node. So for 2 the left child is 4. So the diagonal distance will be, the diagonal distance of parent is 1. So 1 plus 1 is 2. So the diagonal distance will be 2. For right child it will be same as the parent. Then again for left child of 4, 2 plus 1 is 3. For right child it will be same. For left child of 8, 3 plus 1 is 4. Then for right child it will remain same. Let's go here. For left child 0 plus 1 is 1. Then for right child it will remain same. Here for left child 1 plus 1 is 2. For right child it will remain same. Sorry, it is 1. Same as the parent. Here the parent of 11 is 6 and the distance is 1. So it will remain same here. Now for left child here for 15, 2 plus 1 is 3. And for right child it will remain same. Again for right child of 7 is 12, so it will remain same. 7 doesn't have left child, so no need of assigning any distance. Now for 12 left child is 0 plus 1, 1, and right child is 18, it will remain same. So this is how we assign the diagonal distance for each node in this binary tree. Now, so all the distances reflect each diagonal. So for D is equal to 0, how many nodes are there? 1, 3, 7, 12 and 18. So this is one diagonal. 1, 3, 7, 12 and 18. This is one diagonal. Then for D is equal to 1, what are the nodes? 2, 5, 6, 11 and 17. 2, 5, 6, 11 and 17. Then for D is equal to 2, what are the diagonals? 4. What are the nodes in this diagonal? The nodes are 4, 9, 10 and 16. Check 4, 9, 10 and 16. There is no other node. Then for D is equal to 3. The nodes are 8 and 14. Then for D is equal to 4. The nodes are, there is only one node, that is 13. Now let's add these distances. So if we add these nodes for each distance, that is, these are the diagonals in this binary tree. If we add these nodes, then obviously we will get the sum for each diagonal. For example, here 1 plus 3, 4 plus 7 is 11, plus 12 is 23, 23 plus 18 is 41. So that is the sum for the first diagonal. And similarly, we can calculate the sum for each diagonal here. So this is how we calculate the diagonal sum. Now we will see the algorithm for doing this. So let's see the algorithm now. This is the algorithm, and we are going to execute this algorithm on this binary tree. In this algorithm, we are not going to use the diagonal distance, but we are going to use an easier method. So for that method, we are going to use the data structure Q. So let's see the steps in the algorithm. The first step is enqueue the root. So you have to enqueue the root of this binary tree in the queue. So I have enqueued the root, that is 1. Then enqueue null. Then you enqueue a null character in the queue. Go to the third step. This is a while loop now. Inside that loop, P is equal to dq. So you have to dq from the queue. When we dq, we get the node 1. So our pointer P will point to node 1. So our pointer P is pointing to 1 now. So let's go ahead. If P equal to null, but in this case it is not null. So let's not go inside this condition. This is the breaking condition, or when we encounter null, we have to go inside this red square. But right now P is not null, so we directly go to this step. Yes. So initialize variable sum is equal to 0. So the variable sum is initialized to 0. Now, while P is not equal to null, yes, it is not null, then go inside. Sum is equal to sum plus P points data, means data of node P. Yes, so 0 plus the data of that node is 1. So we have added 1 to the sum. Now, if that node, means if this root contains the left child, then we have to enqueue this left child. So if P points left, then enqueue that left child. So we enqueue that left child, and then we go to the right node of P. So we jump to the right node of P. Now P will point to the right node. Now I will tell you the summary of this algorithm, and then we will perform the steps directly. So the summary is that you have to keep jumping to the right node of every node, but while traversing this right child series. So for root 1 or for node 1, the right child series is 1, 3, then 7, then 12, and then 18. While going through this, if you have the left child for that node, means for 3 there is a left child 6, then you should enqueue that left child in the queue. So we will enqueue that child. Yes. Now jump to the right child 7. Does it have left child? No, it doesn't have. Again jump to the right child 12. Does it have left child? Yes. So enqueue that left child. So the summary is that you have to go through the right child series, of every diagonal, and while going through the right child series, if any node has a left child, then just NQ that left child. Yes, now we will execute the algorithm and you will see how we move further. Let's execute it. So our P is pointing to 3 now. So we come here, P is not equal to null, so sum is equal to sum plus data. So we have to add 3 to the sum, and if P points left, then NQ. So does it have a left child? 3 has a left child? Yes, it is 6. So NQ that left child. Yes, and P is equal to P points right. So jump to the right. Now P will point to 7. We have jumped to the right. Yes, now add 7 to the sum and check whether it has a left child. No, it doesn't have left child. So no need to NQ anything and directly move to the right child. So P will point to 12 now. So when P will point to 12, just add 12 to this diagonal or to this sum and check whether it has a left child. Yes, so NQ that left child. So we have NQ'd it and jump to the right. So we have jumped to the right. So 18, just add 18. We have added 18 and we checked that whether it has left child. We have already NQ'd. So we have to move to the right now. The right is null. Yes, this is the condition when in this while loop P is equal to null, and when P is equal to null, we come out of this while loop, and when we come out of this while loop, we again go to the beginning of this outer while loop. In this outer while loop, we have again dequeued and P will point to the dequeued element. So let's dequeue. So when we dequeue, we get null now. The dequeued element is null. This is the dequeued element. So when P is equal to null, this means, this is important now, this means the first diagonal is over, means the ongoing diagonal is over. So you can print the sum here. You can print the sum. When P equal to null, you just print this sum here and you will get this sum equal to 41. So it will print 41 there. Now again NQ null. So you have to NQ another null. This another null is for tracing the next diagonal. This null is going to end the diagonal starting with 2, 6 and 17. Means all the right child series of 2, 6 and 17 will come in this diagonal, and this is the second diagonal, and this null will differentiate this second diagonal from this third diagonal. So the null differentiates the diagonals. So now again P is equal to DQ. This is the condition which is the breaking condition of this code. So when we DQ again, we get 2. So the DQ'd node is 2 now. DQ'd node is 2. Yes. And if 2 is equal to null, which is not in this case, then we would have broken. But now 2 is not null. So this condition does not satisfy. So we come out of this if condition and we initialize sum equal to 0, and now P is pointing to 2 and we again start with this right child series, that is this code. So while P is not equal to null, sum is equal to sum points data. So sum is equal to 2. This 2 means first sum will be 0 initialized, and then we will add 2 to the sum. Now again, if it has a left child, then NQ that left child. So we will NQ 4, and again we will jump to the right series. So we will jump to the right series again. So here again we will come in this while loop. Check what is the right node. 5 is the right node of P, right child of P. When we come to 5, then there are 2 steps to be followed. Check whether it has a left child. No. So just add 5 to the sum. Yes. And move to the right. So now P is null. So when P will be equal to null, we come out of this while loop and we go to the beginning of the outer while loop, and we DQ again. So we DQ. In short, keep DQing and follow the right child series of each DQ'd node. So we have DQ'd. So DQ'd node is 6. Add that node to the sum. So we have added that node to the sum, and check for the left child of that node. It is 10. So NQ the node, left child of that node. P is pointing here now, and left child is 10. So we have NQ 10, and then jump to the right. So for 11, what is the left child? There is no left child, so just add 11 to the diagonal. Now go to the right, so that is null. So as it is null, then we again come in the outer while loop and we DQ again. So we DQ 17 now. So yes, 17 is here. So add 17 to the sum and go check whether it has left child. No. So go to the right. As right is null, we come out of this while loop and we go to the beginning outer while loop. Now when we go to the outer while loop and we DQ, we get null, and when we get null, we have to print the sum as this diagonal is over. Now we print this sum here. So let's do it. 2 plus 5 is 7, plus 6 is 13, plus 11 is 24. 24 plus 17 is 41 again. And we have to print that sum here, and we have to NQ null again for tracing the next diagonal. So I have NQ'd null here. So now when I NQ null there, again I DQ. So again when I DQ, I get 4. So the DQ'd node is 4 now. So here is 4 and P is pointing to 4. So sum will be initialized with 4 now. And we will check with the left child. Yes, it has. So we will NQ that left child and we will jump to the right. So when we jump to the right, we get 9. So we add 9 to the sum and we check whether it has left child. No. So we go to the right. Right is null. As right is null, we come out of this while loop and we DQ again. Now when we DQ, we get 10. So check with 10. Yes. So we have to add 10 to the diagonal. Now when we add 10 to the diagonal, just check if it has left child. Yes, it has. So NQ that left child. So I have NQ'd 15 and go to the right of 10. He was pointing here, so go to the right of the 10. So it is 16. So add 16 here and just check whether it has left child. No. Just jump to the right. As it is null, we come out of this while loop and we DQ again. So now when we DQ, we get null. This means these are the diagonal elements and we have to print the sum. So as we P equal to null, we have to print the sum and we have to NQ another null. So we have to NQ another null here. Now when we NQ another null, just DQ again. DQ'd node is 8. So sum will be initialized with 0 plus 8 now, here also 0 plus 4. So 0 plus 8 now. Now check whether 8 has left child. Yes, so NQ that left child, that is 13, and jump to the right. P is pointing to 8 now, and when we jump to the right, P is pointing to 14 now. So for 14, check whether it has a left child. No, it doesn't have. So just add 14 and just add 14 and jump to the right, that is null. So we come outside the while loop and we DQ again. Now when we DQ, we get 15 and we have to add 15 here now. So 15 doesn't have left child and right child, so we just jump to the right child, that is null, and we come outside this while loop. So when we DQ again, we get null, and when we get null, we know that this diagonal is over, and we print the sum here. And when we print the sum, as we have got null as DQ'd element, we have to NQ another null here. So I have NQ'd another null. I will write it clearly. I have NQ'd another null here. So now again we have to DQ by this statement. So when we DQ now, we get 13. Now P is pointing to 13. 13 doesn't have left child, it only has right, that is null. Right child is also null. So the last diagonal is over here. So the sum of the last diagonal will be 0 plus 13. And here, as we have encountered null here, we DQ again, and when we DQ again, we get null, and when we get null, we have to NQ another null. Now as we have NQ'd another null, when we DQ here, we get null again, and then we break. This means when we get two continuous nulls, these two continuous nulls, this means our all diagonals are over and we have to break from the outer while loop. Yes, this is the meaning, and we have to break and we have to go to the main function. So this is how this algorithm works. I have another video which is named as print diagonal elements in binary tree. If you see that video, then you can understand this algorithm perfectly. Hey friends, please subscribe to my channel as I post algorithm videos every day. And if you want a video on any particular topic, then please mention in the comment below. Thank you.